Hello everyone again. This is lecture 8 part 1 of wave optics. In this discussion, in the last discussion we started with the diffraction concept, and today we will go on to further discussions on diffraction only after the numerical aperture concept. So without wasting any further time, let's begin our discussion directly. I am Sameer Lavankar. Let's begin our discussion. So just before that, a course outline for you. So we started with the introduction, in which we understood what is the concept of wave optics, how it is different from the Descartes theory, that is particle theory of light. Why was there a need for the wave theory to come into picture? The second was about Huygens principle, in which we understood the concept of wavefront, as in if we know the wavefront at some time t is equal to 0, we can find out the value of wavefront or the shape of the wavefront at some time t is equal to tau. Then next was the refraction and the reflection laws of plane wave using Huygens principle, in which we proved the reflection and the refraction laws of light using Huygens principle and wavefront concept. After this, we understood the coherent and the incoherent addition of waves, in which we understood what is the intensity at coherence and what is the intensity at incoherent. And after this completion, we understood that what is Doppler effect. We understood a small significance on Doppler effect, how it is applied in light waves, how it is applied in sound waves, etc. What happens when the source of light source is moving or is stationary. The next was interference of light waves in Young's experiment, in which we understood the application of coherent and incoherent addition of waves, as in the interference fringes are being formed with the central bright fringe and then consecutively dark and bright fringes as we go on, as the path difference increases. In Young's experiment, we understood two types of experiment. One was single slit, one was double slit. Then we understood the concept of why was there a phase locking required for the Young's experiment or for the interference fringes to be formed. After this, we are currently on the diffraction concept. We started with the diffraction, that is what is the significance of diffraction, what is the concept of diffraction, is it just the interference of two diffraction, is the Young's experiment just the superposition of two different diffraction patterns or not. So these all concepts were being understood. Then right now we are on the resolution concept, in which we are trying to find out what is the value of numerical aperture and so on. So now let us move on to our discussion directly. So in the last lecture we understood some of the concepts. These were similar to the optics concept only. So as we know that magnification is V by f. What is V here? V is the distance from the lens at which the image is formed. What is f here? F is the focal length. Also from this directly we calculated that d by f is approximately equal to 2 tan beta, where beta is this angle subtended here. Then finally what we got was, yes, so we got the minimum separation for which the images will be resolved, that is they won't combine into a single entity, will be d min is equal to 1.22 f lambda upon capital D. What is capital D here? Capital D is a complete distance on the, as you can see in the figure. Then f is the focal distance, you know, lambda is the wavelength of the light, else everything is known. So d min is calculated like this. Also we can get similarly that 1.22 lambda. So how does this we calculate that d min is equal to 1.22 lambda upon 2 tan beta. So as we know that d by f is approximately equal to 2 tan beta, so we can just directly calculate it as, let me write here, so 1.22 f upon d by lambda. So here in the place of d by f, as we know that it is equal to 2 tan beta, we can directly write it as 1.22 lambda upon 2 tan beta. Also when the beta is small, we know the mathematical approximation that let me write it here. So when theta is small, then we can approximate sin theta approximately equal to tan theta approximately equal to theta. Please make sure that here theta will be in the radians. So as the theta angle subtended is very small, then we can write that 1.2, this is also equal to 1.22 lambda upon 2 sin beta. So this is only the, so how did we get this? We just get this because we know that d by f is approximately equal to 2 tan beta. How is this thing calculated? This is just simple trigonometric explanation applied on this area, on this triangle. Let me denote the triangle also here. So this is the triangle on which tan beta was being applied. Okay. So this was explained in the previous lecture only. So after this we understood a concept called as numerical aperture. So what is numerical aperture? So generally in general sequence always air is the medium which is surrounding the convex lens, but sometimes if air is not the medium, then for finding out the d minimum value for which the images are resolved, we will find out that value equal to 1.22 lambda upon 2n sin beta. So what is n here? N is nothing but is it written? Yes. So n is nothing but the index, medium of refractive index n. Therefore, when we find out this value, so we got that n sin beta is equal to numerical aperture. So please remember this formula, please remember this definition, that it is equal to n sin beta. So it is numerical aperture. Okay. So the product n sin beta is called a numerical aperture and is sometimes marked on the objective. Sometimes it is also marked on the objective. So these things were done, I guess, in the last lecture only. The resolving power of the microscope is given by the reciprocal. So this concept was also being done. So let me just move on to next discussion only, because these all things are done. Okay. So now let's move on to today's discussion now. So please look over here carefully. Notice that it is not possible to make sin beta larger than unity. It is quite evident, as we know that this is just simple mathematics, that every time sin beta will be always between -1 and 1 with 1 and -1 included. So it can't, so therefore sin beta cannot be greater than 1. Sin beta cannot be greater than 1. So it is not possible to make sin beta larger than unity, quite evident. Thus we see that the resolving power of a microscope is basically determined by the wavelength of the light used. So what does it try to say is, what is resolving power? So just we have to just go here. So it is saying that resolving power, we know that resolving power is inversely proportional to 1 by d min. As it is inversely proportional to 1 by d min, therefore we got the concept that it is directly proportional to, and it is, or let us say I will write it as sin beta, also directly proportional to the value of refractive index, and also proportional to directly value of or inversely proportional to lambda. So as it is concluded here that we cannot change the value of beta greater than unity, hence the only concept to change this resolving power is nothing but wavelength. So if we change the wavelength, simulate or modify the value of resolving power. Thus we see that the resolving power of microscope basically determines the wavelength of light used. A telescope produces image of far objects nearer to our eye. So that is a simple application of telescope. What does a telescope do? It just so if I make a typical diagram, so let us say this is a diagram, let us say this is the object. So the object's image is being captured at this position. Therefore what telescope does is it tries to bring the image nearer to us. So a telescope produces images of far objects nearer to our eye. Therefore objects which are not resolved at far distances can be resolved by looking at them through a telescope. So the things which we cannot see clearly, such as moon, such as stars, such as planets, such as comets, etc., which cannot be seen by naked eye very clearly, a very sharp image, then that can be viewed using a telescope. Similarly, a microscope on the other hand magnifies objects which are near to us and produces their large image. So this is just an application which is opposite to telescope. What does a telescope do? Please be clear on this concept. So what does a telescope do? Telescope brings the image of a far object to near us, and what does a microscope do? It magnifies the image. It does not bring the image back, it just magnifies the image which is already near to us. So it's the main application of microscope is magnification, and main application of telescope is just to bring the image near to us. So we may be looking at two stars or two satellites of a faraway planet, or we may be looking at different regions of a living cell. So this is an example of a telescope, and this is the example of a microscope. So in this context, it is good to remember that a telescope resolves whereas a microscope magnifies. So this is only the thing which I was trying to convey to you. Please make sure I will just write it here also, so that it is a revision again. So what does a telescope do? Telescope has an object which is far away. Let me write it here, so it will be much clearer. So let us say there is an object which is far away. We pass that object through. So what does a telescope do? Like if we have a telescope, then telescope creates an image which is near to us. This is the application of telescope. What does a microscope do? Again there is an object, but it is near to us. When we pass it through microscope, it just magnifies it. So magnified object is visible. Magnified object is visible. So please make sure here no image is being put near to us or away from us, only the image is magnified here. So it is good to remember a telescope resolves whereas a microscope magnifies. So here a resolving concept is coming to picture in the case of telescope, but there is nothing called as resolving in microscope, as long as we are just focusing on magnification concept. Okay. Next is, so what's an aperture? In the previous lectures also we are considering a concept called as aperture. So aperture can be just in simple terms can be understood as a slit or a hole. So an aperture, that is a slit or a hole of size A, so I am assuming it is a size A, illuminated by a parallel beam, sends diffracted rays light into an angle of approximately lambda by A. So this is a simple concept which we already understood in the concept of single slit diffraction pattern also, that whenever a pattern whenever parallel lights come into a slit or a hole, then it diffracts. This time we got that angle which is approximately equal to lambda by A. This is the angular size of the bright central maximum. Again we understood this concept in previous lectures only, so there is no point to again understand this. We just know that when theta is equal to approximately lambda by A, we can get central maximum as long as it is diffracted inside. If it is diffracted away, we may get something different, but as long as it is diffracted inside, we will get a bright central maximum. In travelling a distance z, the diffracted beam therefore requires a width z delta by A due to diffraction. So this is the simple concept of diffraction here, that as we move, let us say this is the distance being z moved, then when the distance z is moved, then the width, it acquires a width, it is z lambda by A due to diffraction. At what z, so now the question is being asked that at what z the spreading due to diffraction becomes comparable to the size A of the aperture. So it will happen when it follows approximately equate z lambda by A with A. So we just need to find out the value of z. So let us say z is the variable here, similar to x, we just need to find out the value of z such that z lambda by A, such that this width is equal to A or approximately equal to A. Then just simple mathematical calculation gives you z is approximately equal to A square by lambda. What it is A square by lambda, what is its significance, I will convey to you. First let me just iterate this again. So this concept is done. This gives the distance beyond which divergence of the beam of width A becomes significance. Okay. So what was the thing, let me explain you using a diagram here. So let us suppose this is the screen, and let us say this is the distance z being talked about here and travelling a distance z. So let us say this is the distance z. Now if a slit is being formed here, let us say it has a width A, and let us say we are comprising it at some angle theta. So this is the distance z and this is the width which is talking about here. So when this gives the distance beyond which divergence of the beam of the width A becomes significant. So what does it happen is, we are just calculating a distance which is z, which is approximately equal to A square by lambda. What will happen at this distance? The divergence of the beam of width A becomes significant. So in that time we can actually see the diffraction pattern being occurring. So what is the distance? Because it is happening in very minute distances, it is not even visible to naked eye, but it will happen, it will be visible to us when the distance z has taken place, or when the distance z is at least this much. How much? That is approximately equal to A square by lambda. So when z is approximately equal to A square by lambda, we will see the diffraction pattern, that is the dispersion will be occurring as it is written, sorry, divergence of the beam of width A will become significant. Okay. So therefore A square by lambda, so just remember this, we know this quantity is ZF called as A square, Fresnel distance, which is denoted by the equation ZF is equal to A square by lambda. So for exam you just need to remember this, that ZF is approximately equal to A square by lambda. Above equation shows that for distances much smaller than ZF, the spreading due to diffraction is smaller compared to size of the beam. So quite evident, as I already told you, the diffraction pattern which will be visible, because the distance is less, hence complete width is not being utilized, and because complete width is not being utilized, therefore diffraction pattern is very small as compared to, because it is being compared to the size of the light. As we know, what is diffraction? Diffraction is the phenomena due to which the light is bent. When it is bent, only during an obstacle which is of the order of the wavelength of light. Therefore the similar concept is being used. So this is only and only possible that when the spreading due to diffraction is smaller as compared to the size of the beam. So when z, let us say I consider a z which is less than ZF, then at that point what will happen is, because the diffraction, spreading due to diffraction is very less, why it is less as compared to the size of the beam. What is the beam being talked about here? Beam is the light source here. Okay. So it becomes comparable when the distance is approximately ZF. So quite evident, it becomes comparable because ZF is approximately calculated for the wavelength of light only. So when it comes approximately equal to wavelength of light, the size is being encapsulated and hence we will get a diffraction pattern. For distances much greater than ZF, the spreading due to diffraction dominates over that due to ray optics, that is the size A of the aperture. Above equation also shows that ray optics is valid in the limit of wavelength tending to 0. So what does it try to say is, why do we not consider diffraction when we studied the ray optics concept? So in ray optics concept, this value of Z A square by lambda is so much small that we assumed it to be 0 only, and that's why the complete concept of diffraction is being neglected. Here what we try to assume is, we are assuming a value of ZF such that value A square by lambda we get a distance such that we get a diffraction pattern. Therefore this is the diffraction pattern talked about here, and hence when the size of the aperture being talked about is A, then at that point diffraction dominates. Therefore for wave optics to come into picture, this is one of the application why wave optics came into picture, and hence we understood the concept of diffraction. So this was the final concept of validity of ray optics which I needed to convey. So in this concept we just need to remember that Fresnel distance which is equal to A square by lambda, and hence this concept is completed. So after diffraction concept, let us move on to the polarization, that is the last concept of wave optics. What is this polarization? What do you mean by Polaroid? What is this polarized light? Why it is calculated? What are the different ways to get a polarized light, etc. We will study in this concept. Okay, so first of all let me try to understand, so let us suppose, please look over here, as we know that light is a combination of electromagnetic plus magnetic wave. Any wave is a combination of electromagnetic and electric and magnetic waves, and which are perpendicular to each other. So if I make a diagram just to explain to you, let us suppose this is the direction of propagation of light wave. Let us suppose this is the direction of electric waves in the, let us say if I write it like this, let us say this is the direction y, this is the direction of propagation which is given as x, and let us say this is the direction z, x, y, z. So this is the explanation which I need to convey. So this is the electric signal, let us suppose this is the electric signal. And let us suppose, let me change a different color, let us suppose this is the magnetic. So please look over the diagram very carefully here. So here what happens is, let us suppose this is the electric signal, this is the electric wave or electrical wave. Let us suppose this to be magnetic wave. So the basic concept of light says that it is a combination of electric wave and magnetic waves, and the light wave is suppressed or it possesses in the direction of propagation as long as the vibration happens. For clarity, let us suppose what we suppose is, when the light wave is moved on from point A to point B, only the vibrations which happen are being understood in the electrical wave only. So for example, let us just remove this magnetic wave for us. So if we just try to explain this, if our eye is, let us suppose here, then this direction can be understood in this way. But so this is one of the explanation, or this is one of the way in which we can tell that the vibration is happening only in this direction, either in north or let us say above or below. But similarly in the another cases, if the light is not only in the single scenario, it can be in perpendicular waves or in 30-degree angle or 60-degree angle. So let us suppose I make several different arrows like this. Now after these arrows we can, as these are forces only, we can just make components of them and we can find out the values in the x and y plot. So let us suppose I am taking an x and y plot like this, then just making components of them in the x and y direction gives you the values of electrical signals in this way. So, this is nothing but the depiction of how a unpolarized light is being resolved. So, this can be understood as an unpolarized light. So, for this class let me stop it here only. I will again start with this concept again, what is unpolarized light, what is light, what is this happening. Let me try to revise it again in the next lecture. Let me stop it here only, but for now just let me explain that this is the light propagation of light, in this direction it is happening, and then this is electrical wave, this is magnetic wave. We are assuming that the vibrations are happening only in electrical wave, therefore from when we view it from this direction we can find it in a straight line above and below only, but because the light is a combination of different wavelengths which can be inclined in any angles, therefore it can be in this sequence. When we try to take the components you can find it as this denotation. This denotation is nothing but of unpolarized light. So, let me stop it here only. Thank you.